Okay, so we'll start today's lecture. Um, so about 20 students are missing, or maybe 19 students are missing. So how are the other kids doing? I mean, some of you probably are group mates with some of the students are not showing up. So are they okay, doing okay in the course, or all your group members are here? Okay. Okay. So let's continue with where we left last time. So last time I did not explain what's the difference between ridge and lasso. Okay, that was the choice of lambda, which was, okay, let me just write it. So today we'll look at, let me just enumerate what we'll look at. Second, okay, classification, in which linear regression, MDK. Okay, so these are the topics we'll try to cover today. So mostly try to finish up linear models with regression. That's what we were doing in the past 2-3 lectures. And then we'll look at some linear models related to classification. So what does linearity mean in classification? It has something to do with decision boundary, so we'll kind of revisit that. Okay, and then towards the end we'll again kind of, we already know cross-validation, so we'll just put it in the context, broader picture of model selection and assessment. Okay, so so some of these topics you might have already seen. I don't know, did for example, those of you who are taking 572, did they cover logistic regression already? Okay, they covered logistic regression. Okay, so we'll look at logistic regression. So did they also cover linear discriminant analysis, LDA? Okay, so we'll look at logistic regression, LDA, as almost the same thing. Maybe even actually, if we have time, we can also talk about naive-Bayes classifier. Did they talk about naive-Bayes classifier in the other class? Okay, so we'll totally skip this one in this class. Okay.
Does that say assessment?
Yeah, assessment. Just evaluation. So what we've already seen cross-validation, but we're just using.
I just couldn't read it.
Okay. Okay, so let's start. Okay, so if you remember ridge, regression, the origin of the names and techniques, sadly I don't know too much about it. Ridge regression, I guess, comes from some initial work from geophysics, I think, and maybe even signal processing. Lasso actually is a short form for a long name, some statistician scale, least absolute shrinkage and selection operator, but it's not really very critical what the name means. The optimization view that we saw last time was that these are basically trying to solve, let's see, okay, let me just write residual sum of squares of a model beta plus lambda times sum over j of beta j square, and this one lasso was residual sum of squares of beta plus a different lambda here, it's a different model class, j of absolute value beta. Okay, so this was pretty much the difference. these two are also called, the first one is called L2 penalty, actually L2 square. So you may see L2, actually there's a notation, right? Last time we said it's like this, right? Of whatever vector in the inside. Here it's beta, which is p-dimensional. And then this is also called L1 penalty. So you subscript using 1. So if you put a beta in here and use this symbol, it essentially just means this. And if you use this symbol squared and this inside, without the square there will be a square root, which is the the length of a vector.
The subscript with the 1 and 2
Yeah.
on the normal signs.
Yeah.
What does that mean in this stuff?
What do they mean? These are notations for these definitions, these penalties. So this is called the L1 norm, and this is called the L2 norm. So for vectors you can define norms, right? So you can define different norms for a vector space. Okay. And norms also implicitly define what is known as the distance for that vector space. So if it's an L2 norm, then the distance is the usual Euclidean distance, which you know that if there are two vectors, then you element wise subtract, square them, sum them, and take a square root. Right? That's the distance between two vectors. Yeah. Let's not worry too much about it. Yeah. So they look very similar. So both are, there's a square here, but otherwise, these two are norm penalties. Okay. Then the question arises, what's the big difference? They almost look the same. So lasso has some nice properties. The reason. Okay. So first of all, both these are biasing your linear model. So you're searching for betas. So you're still, you're assuming that the conditional expectation of y given x is equal to x is actually just beta transpose x. So you're assuming something like this, and you're saying among all the linear models that I can choose, I'm going to choose models which probably have small L2 norm or small L1 norm, depending on which model, which biasing technique I use, basically ridge or lasso. Okay. So it's basically further biasing, just like subset selection. Right? It's further biasing your linear models, which you want to pick. Okay.
So this conditional expectation is similar for both of them?
I mean, this is true for all linear models. Right? Linear models are basically assuming that the regression function is linear.
Mm-hmm.
Remember regression function from lecture 2? KNN was not assuming any linearity. It was just saying we're going to approximate directly using a bunch of neighbors in mind for any query test point. Okay. So this is true. This is what all linear regression, for regression, all linear model classes kind of try to approximate this. In the sense you can always define some other things, but linear models typically approximate this. And ridge and lasso. So within linear models, vanilla linear regression doesn't bias anything more. It just says let's minimize the sum of squares. We had a closed form expression for beta hat. Subset selection says, okay, I think there may be too many. Some of the feature coordinates may be irrelevant. So let me kind of shrink the number of features. Okay, that's biasing further. So I'm still looking for a linear model, but I'm doing bias. I'm reducing the number of features. So my training error will increase because I'm reducing the number of free parameters. Like if originally my number of features was 100, but I choose a subset of 10, I have lost 90 other coefficients that I could have used to further reduce my training error.
And that is the concept where ridge and lasso difference.
Yeah, that's bias, and no, not yet. Difference I'll come to. These two also bias your model. Within the models, they want to pick those models which have low L2 norm square and L1 norm. Okay. These are biases. So it's basically, you want this is a score for any model beta, right? There's a score. This is a number that you're associating. You're just associating. You're trying to get. So originally you were just minimizing the sum of squares of beta. Okay, so that's pretty much the scoring function for your model. Here we are saying I'm going to also ensure that whichever model I pick, that model's L2's norm square is not big. Right? So maybe there are two models. One model may have small sum of squares of this thing, and the other model may have larger numbers. Then you're going to pick the one with the smaller coefficients. Okay, that's called bias, right? And we saw its impact last time. So for ridge, we actually saw that the in-sample prediction, which is given by matrix X times beta hat, okay, was essentially equal to some sort of some coefficients times uj, where j is equal to 1 to p. Okay, so these coefficients, if you remember, I had this expression. In fact, the right expression was sum over j is equal to 1 to p of dj square divided by dj square plus lambda times uj transpose y vector times uj. Okay, so basically what I'm saying is the coef that I wrote here just as a short form is essentially, if you just go back to the lecture from last time, it was dj square by dj square plus lambda times uj transpose y. So some coefficient there. All I'm saying is, so for ridge, we said in sample prediction. So this is going to be n cross 1 dimensional vector, is a linear combination of the right singular vectors of your SPD decomposition of the data matrix. Okay. And it turns out that uj, I mean, so how do you kind of think of uj? What is meant by left singular vector of your data matrix? So what does uj just mean? Uj is just actually yet another sum of let me call the coefficients alphas, alpha k xk. Okay, where xk, I'm putting a tag at the top, which means that what is the interpretation of the left singular vector of the SPD decomposition of X? So X data matrix is equal to U matrix times D matrix times V transpose matrix, right? The U matrix is U1 to UP. These are the column vectors, right? Now, so when you do this SPD decomposition, each U vector here, this column vector, is essentially a linear combination of the feature vectors, okay, the n-dimensional feature vectors. So this is what the interpretation is. So uj is just some combination of your feature vectors. Okay, this is a repetition from last time, so I don't want to spend too much time on it. But so uj's are like this, and my prediction is going to be some other coefficients times uj's. Okay, the p such uj's, so I'm going to just add up all these p uj's, but different weights in front of them. And these coefficients inversely depend on lambda. Okay, so roughly what I'm saying is, if you have large lambda, then somehow I'm kind of gonna kill some feature vectors. Okay, can you see that? So I can just substitute the definition of uj here, right? And coefficients, I said, is somehow proportional to 1 by is proportional to 1 by lambda. Okay. So when I you can see that, right? So this coefficient is essentially this term here. Let me write this uj. U, and this is a y. Okay. Anyway, the coefficient here, forget about this part. The coefficient here has a inversely related to lambda. So what I'm saying is, if you pick a large lambda, right, then there's going to be lambda in the denominator for one of the terms, right? I mean, for all the terms there will be lambda, but for some terms there will be a higher impact. I think we saw that last time. When dj's are small, there will be higher impact of lambda in the denominator, and there will be a corresponding uj. And uj is nothing but a sum of xj's. So there will be some corresponding xj's which will be downvoted. It's basically doing something like subset selection. Okay, when you pick a large lambda, it's trying to do something like subset selection. It's trying to set some betas close to 0. not all betas close to 0, as you saw in the optimization version. It may look like if I choose a large lambda, all the betas are trying to be pushed down to close to 0 because there's a penalty, right? The bigger beta I pick, the larger is my total scoring for my model. It may, just by looking at this, you may think, okay, if I choose lambda large, all the betas are being pushed down to 0, but they are being pushed down to 0 in an unequal way. Okay, and that's given, and that's where we use the SPD to kind of understand which coefficients get pushed down more. Okay, and that happened to be we first had to look at UJs and then look at those coefficients of UJs get pushed down more where the corresponding DJs are small, and DJs correspond to these sample variances in the principal component directions. Okay, there was a 2D picture, right? So there was a picture. There's a bunch of data points. There was so this was let's say V1, and let's say this was V2. So these were principal component directions, and DJ is essentially like variance in this direction. So you project all these points. So you'll have one-dimensional numbers, variance of those one-dimensional numbers. Okay, a set of one-dimensional numbers. We defined this last time.
So do we want to try and keep lambda not too large? Then?
So you're gonna make the choice of how to pick lambda based on cross-validation.
Okay.
So just like subset selection is a choice of which subset to pick ultimately. So you are scoring for every choice of subset, you are getting a proxy, right? You're getting an estimate of the EP, right? Expected square prediction loss. So here also you will try for different lambdas, and then pick the best, one lambda for which you will have the best cross-validation score. But let me get to lasso. So lasso seems very similar, but unfortunately there's a couple of differences. One is that lasso doesn't have a closed form expression. Actually, let's not worry about closed form expression. So the difference is that difference is in terms of how the beta j's are set to 0. Okay, the difference, and that's illustrated in a diagram. Okay. That's illustrated in this diagram. Okay, so let me write lasso here. So I'm going to draw two pictures, lasso and ridge. Okay, so lasso actually has this type of a constraint, right? Sum of pj, j is equal to 1 to p, and ridge has sum up to p of pj square, right? So these constraints. So remember last time I said this is less than equal to t is essentially the equivalent version of ridge and lasso, right? There was the lambda times this term is the same as saying I want to minimize residual sum of squares such that this constraint holds. Okay, the betas are within a budget, essentially. Whether the budget is defined using L2 norm square or L1 norm is the difference. Now these sets, so this is a set, right? So this is like saying, tell me what betas satisfy this constraint. Tell me what betas satisfy this constraint. In 2 dimension, it turns out that the betas that satisfy that constraint fall inside a diamond-shaped area. Okay. These are the betas which satisfy this constraint. Okay. Turns out that this is the picture, and this you can see. This is like a equation for a circle in 2 dimension, right? So x square plus y square is less than constant, so you can kind of intuit that this is going to be like a circle. So these are the two areas. So it's really saying pick a beta inside this and pick a beta inside that. So the difference between lasso and ridge is essentially these sets. Okay? You're trying to pick a model from this side or this side. Now there's also residual sum of squares. Okay, so that's the second term. That's the objective actually of beta. That turns out to be, we saw that it was essentially in the vector notation, it was y vector, which is n dimensional, times x matrix, which is n times p dimensional, times beta, right? 2 square. Remember we did this in the second lecture. The summation residual sum of squares definition was just this, and we did vector calculus as also in the class. So this, let's say, so this is the objective. Let's understand its how does this function look like in 2D space. So what I'm going to do is look at what are called contour plots or contour lines, which just means that, okay, for what values of beta is this constant C1, and what values of beta is it a constant C2? Tell me, like, this is a space, this is a beta space, right? This is beta 1, this is beta 2, okay? Beta 1, beta 2. So we are plotting things in beta space. Residual sum of squares is also saying, it's giving a number for beta. So tell me, what are those betas for which it gives the same number? That's going to be a contour plot. Okay, it's basically saying. So this is the definition of residual sum of squares. I want to know for what values of beta this is equal to a constant. Okay, right. So that's going to be something like this. So for some betas, for some constants, these will be the betas for which it will have the same residual sum of squares error. Okay. So, okay, let me kind of first draw the contour plot. It's something like this, and there will be the same thing on this side. Okay. Contour plots are just top view, okay, of how the residual sum of square function looks like. It's just saying this. First of all, residual sum of squares is a quadratic function of beta, right? It's a quadratic function of beta, which means that essentially, how does a quadratic function look like? It's a parabola, right? In one dimension, you can kind of just plot it as y is equal to x squared. It's a quadratic function of x, and so it's a parabola. In 2 dimensions, how does a quadratic function look like? It looks like a ball. Like if you really want to imagine in 3 dimensions, like 2 dimensions, your beta is in 2 dimension, but the function is going to be like a ball. Okay, and if you look at the top view, how are you going to visualize the top view? You're going to just join the points which have the same value. Okay, so this is just a visualization of a ball. So it's like the better picture would be, think of a ball like this in a 2D space. Okay, let's say beta 1 and beta 2, and this is the 3rd dimension. We are just connecting all these points. Like. You're just completing the circles along the ball, pushing them down. That's the contour plot. Okay, this is the plot. It's just saying, see, that was our objective, right? To minimize residual sum of squares, and we had the budget version where, let's say, the budget is like this, some t and some t, and we said the budget space, we are searching for betas which fall inside this, searching for betas which fall inside this, and so since we are searching for betas which only fall inside this, we have to score the betas inside this only. Right? We only care about scoring betas which are inside this. Let's say the true beta, let's say the linear regression beta, where there is no restriction on which beta we want to pick, is actually the minimizer of just the residual sum of squares. Okay, so the ball will have an end point, right? I mean, the ball will have the lowest point. Let's say that's this point. Okay, let me put a star there. That's the point. Okay. And then at the remaining points, it's going to be higher residual sum of squares, right? I mean, there's one minima in the ball, and every other point will be higher than that. Now, you're just trying to search for betas only inside this. So let's look at where does this curve intersect this diamond region. Okay, it's gonna, maybe it'll intersect here, maybe it'll intersect somewhere else. In this diagram, I've just drawn it in a illustrative way. So it's intersecting over here. Okay, and in this diagram it's intersecting over here, so let's say some beta over there, intersection region. Okay, yes, we only want to get a beta from inside, and so we're gonna, if you had another contour plot, those betas maybe on this contour would have higher residual sum of squares value, right? So we are saying we want to only search for betas inside this, but we want to minimize ratios from our squares. That means that we're going to pick this point essentially. Okay. And then this side is also the same. We only want to pick a beta or model inside this. But if I consider bigger and bigger contours, those values will be higher. The ball is expanding, right? Because this is the lowest value. That's the bottom of the ball. So we were again going to look at some intersection combinations. So what happens is, because of this scale, it's like a diamond, or a square in 2 dimensions. In higher dimensions, it's going to be like a diamond. Okay, in 3 dimensions, you can imagine how it's going to look like. For every coordinate axis, there's going to be one sharp point like this. Okay. And these guys will not have sharp points. So what will happen is, this guy is more likely to, in the intersection point, this guy will more likely lead to some betas being 0. Okay, so for example here, beta 1 is 0 and beta 2 is, let's say, 1. Okay, let's say this is a unit, let's say budget t is equal to 1, which means that this point is -1, 0, this point is 1, 0, this point is 0, -1, and this point is 0, 1. Okay, so you can just check that, whether that's true or not. But what I'm saying is, this type of diamond structure leads to betas being set to 0 at the intersection more easily than here. Here betas will not be set to 0, but they'll be low. Like for example, here beta 1 is small and beta 2 is large. Right? So that's the impact of having an L1 or lasso penalty. Sorry, lasso version. Okay, it'll set exactly, lasso sets some coefficients. Oh my God, my handwriting. Exactly 0, whereas makes them close to 0. A ridge makes them close to 0, that we saw because of the SVD version last time. Lasso sets coefficients close to 0 because of this interpretation. Okay. Any questions about this? Yeah.
Would you consider our ridge subset selection since you might be going completely 0?
Yeah, I mean, it's a soft version. Both of them are soft versions of subset selection. Instead of choosing over all subsets, which are like, it's called discrete in nature or combinatorial in nature. So you're choosing sets, right? Which are like, last time we saw that choosing sets is essentially the same as, let's say, y is equal to beta 1 times x1 plus beta 2 times x2 plus beta p times xp. We said choosing sets is essentially the same as saying setting explicit betas to 0, right? 0 times x1 would be exactly the subset x2 to xp, for example. Ridge and lasso both are trying to say, let's not explicitly choose sets, let's do some continuous optimization. Let's just prefer things, add this penalty, this term, these two terms here, into the objective, or the equivalent version as constraints, and choose these sets in a parsimonious manner by just tweaking lambda. So that's the only control, rather than choosing sets. And so that's why they are essentially subset selection, ridge and lasso. All three are biasing your linear models. Lasso and ridge are biasing in our approximations to subset selection, or not approximations, but equivalent to subset selection in terms of biasing. But they are only, like, the parameter that you can choose is just lambda, not explicit sets. Okay. And the difference between ridge and lasso itself is that is the nature of the set, nature of this model space where you're searching for the right model. In 2 dimension, it looks like, okay, what is this? It's just a slight difference between this set and this set. In 100 dimensions, you can't visualize, but this guy will have much more peaky, it will have much more corners. Like, let's call these corners. It will have much more corners than this. Definitely doesn't have, has infinite corners, for example. So this set will have a much better impact in terms of setting betas to 0. Okay.
Do we always get a smooth contour stack when we do stack, because we have to worry about
yeah, these two problems are convex. So ridge and lasso, when searching over beta, you're basically searching over the ball. So residual sum of squares is just a ball. So you will just have an optimal, you will just have a single beta hat. That's what we saw. We in fact took the derivative, set it equal to 0. That's how you got the optima. If you took at the second derivative, it will have the right sign, so you can say that it is a global optima. Okay. So anyway, this is a ball structure for residual sum of squares. So it will, it's a convex problem. There is no local minima stuff. Any other questions? Okay. So let's look at now classification, and the first. So we're going to look at 3 or 3.5 things, and classification happens to be. So let's see. The first method we're going to look at is. The first method we're going to look at is how to do classification using just linear regression. Okay, so you can use. So once you know linear regression, you can do a lot of things. So we look at how to do classification using linear regression, and the idea is quite straightforward. So let's say we have a qualitative output G. Okay, takes k values. So G takes values from 1 to k. Okay, this symbol just means the values that G takes belongs to this set. Okay, belongs to, I guess, is the short form, and typically, like when you say y variable, y output variable belongs to real line, for example. Real lines are represented using R. Just a short annotation. It's just that this variable is quantitative, so it takes real numbers. This qualitative variable, since it's qualitative, it's going to take k values. It's classification setting. And so first method, linear regression. It's going to do the following. So if you remember the best classifier, which is the base optimal classifier, just like for regression there was this expectation of y given x is equal to x, right? The regression function. Here the base optimal classifier is just this probability of G is max over let me just put a k. Max over L is equal to 1 to k of G is equal to L given x is equal to x. This is the definition of the base classifier, right? Remember there was this equivalent thing on the regression side with the expectation of y given x is equal to x, right? This depends on the distribution of p of x comma y. This also depends on the distribution of g and x. In fact, the conditional distribution of g given x, right? Any confusion? Are you guys lost? No. So this is the base classifier, and linear regression, what it's going to do is it's going to say, okay, let me just approximate p of G equal to L given x is equal to x as a linear function. Let's just call it beta L transpose x. I guess since x is equal to x, beta transpose x. So this is what linear regression version says. Okay. So it's saying basically, I know base classifier is something like this. If I knew the joint distribution between G and X, then I know the conditional distribution between G and X, which is probability of G is equal to something given X is equal to X. I know all these conditional distributions if I knew the joint distribution. Now linear regression, just like in the regression case, it was saying, okay, let me approximate this thing that we cared about if we knew the joint distribution as equal to beta transpose X, right? Beta transpose little x. Here we're going to say I have k such conditional distributions. I'm going to assume that these k such conditional distributions are actually linear. Okay. That's the assumption that linear regression makes. So first of all, you see beta has a subscript L, which means that I'm thinking of L such, I'm going to think of beta 1, beta 2, all the way to, I'm using beta L. Okay, let me put a arrow, sorry, bar below to say these are vectors. Oh, okay. Whole classification. Yeah. Sorry, not L, but so I'm going to think of k p-dimensional coefficients. So all I'm saying is I want to approximate this with this. And what is this? It's just saying what is the probability that the class label is L given my data point, right? And so my training data is actually just gi comma xi, right? Sorry, xi comma gi. I is equal to 1 to n. So I have n observations. I have xi's, which are features, which are p-dimensional, and gi, which is the class label. Okay. Now, what I'm going to do is for each gi, I'm going to create a vector. For each gi, I'm going to create a vector, which is going to be zeros at all positions except the position where it is actually equal to gi. So except maybe gi is equal to L. Let's say gi is equal to L. Then the Lth position you're going to set it equal to 1. Okay. This is going to be a k-dimensional vector. This is called one-hot encoding. Okay. So this is just the assumption. Now let's get back to how to actually use linear regression to actually get the hats over here. So how does it tie back to my data? Because I said I'm going to approximate this. It's not fully clear how do you do that, right? So given data, what I'm going to do is for each label, I'm just going to create a vector which is going to be k-dimensional. For each label, there's going to be a k-dimensional vector, and in each of those vectors, every entry will be 0 except for the Lth entry. If gi is equal to L, then the Lth entry will be 1. Let's say gj, the next, some other observation. Maybe it's equal to the first label, then the first entry will be 1, everything else will be 0. It's just called one-hot encoding. Okay. And in fact, I think did we look at this in when we were dealing with categorical variables, right? Or no? We haven't seen categorical variables. Like if you remember, there was I don't know if I mentioned this. Like if you had a variable xj, which was saying which will take values, cat, dog, or fox, then you would create 3 such variables potentially, x1, x2, x3, which would take 3 values. X1 would take a value. This is a variable. So let's say my observation actually has cat here and a cat here and a dog here. Then x1 would be 1, 0, 0 for this observation. And for this observation also it will be 1, 0, 0, and for dog it will be 0, 1, 0. Remember, it's just saying if I have a categorical variable, how am I going to use it in my regression? You have to kind of transform it into something else, and that's going to be if there are three labels or 3 values that it takes, then I'm going to create 3 variables, dummy variables. So this is called one-hot encoding. Same thing at the output side, input side. If it's going to be cat, I'm going to say my first new variable is going to be 1. The second and third new variables are going to be 0. For that observation, maybe it's observation 1. Maybe for the second observation there's also cat again, then again will be 1, 0, 0. Third observation has dog instead of cat, so appropriately I'm going to set the x2 to be 1 and x1 to be 0 and x3 to be 0. And eventually if there is an observation with a fox in it, then it will be 0, 0, 1. That's one-hot encoding. Okay. Is there any question about one-hot encoding? Okay. You must have seen this, some of you must have seen this in the other course maybe. Yeah. Do ask questions if you're not following at all. It looks as if I'm going too slow, which means I may have to accelerate. Is this very familiar with you guys? No. Okay. How many of you are fine with this one-hot encoding? It's not a very difficult concept, but okay. Okay, so let me complete the story of how to use linear regression with classification, because it's not really difficult. So given data, you just do one hot encoding on the output side, which is, if you have k labels, k dimensional vectors for every observation, which means that now you actually have a data. You'll have a data matrix X, which will be like this, right? You'll have, let's say P, it's going to be n times P, the usual thing. On the input size, you had G's originally, but now I made it into k dimensional vectors. So I'll have a Y matrix now, which is going to be n times k dimensional. So each row here would be, one entry will be 1 and all other entries will be 0, right? According to the class, right? Now, how to use linear regression? There are two ways. One is to just think of this as now a linear regression problem. So you have y's and you have x's, right? And you can just find a beta matrix. So now you're saying I want to find a y variable, right? Y variable, which is which is k times 1 dimensional, okay, is equal to x, which is called beta transpose x variable, which is p times 1 as before, and beta is going to be k times p, okay, or beta transpose is going to be k times p. Right? If I think I said last time, if your output variable, you're only predicting one output variable, then it's just going to be this 1 cross 1. Beta is going to be 1 cross p, the p coefficients, and x is going to be p. X is just the feature vector, which is p dimension. Now, if you're predicting two things instead of one thing, right? Your k will be 2. Just think of linear regression, forget about classification. K will be 2, and you will say, instead of one set of coefficients, you will get 2 coefficient rows, essentially. K will be 2, so beta will now be a matrix. And I think I mentioned it in passing that even if the model is like this, even if the number of outputs are k instead of 1, the linear regression models, the best model still is like something like this: beta hat is equal to x transpose x inverse x transpose y, okay, n cross k here, and so beta is going to be p cross k. Okay, same formula. I mean, there's nothing changing here. All I'm saying is the last thing that you had is a single vector in your regular linear regression things that we saw in the past 2-3 lectures. It's going to be a matrix, and so beta is also going to be a matrix. Just in terms of dimension matching, you can see that this is true. And in fact, if you actually write this as residual sum of squares, and subtract this, take the this transpose the other thing, minimize that, and all that. If you do that, it's the same thing. Don't worry about doing all that. I'm saying increasing the dimension doesn't change anything qualitatively about linear regression. Okay. And so now that we change our output qualitative variable to this k dimensional vector, now we can just plug this into this formula. Right? You have the y matrix, you have the x matrix. You have to put it in the y matrix. Sorry. These are all matrices, by the way. So you just plug those two in here, you'll get a beta hat, right? And this beta hat is p cross k dimensional. And if you remember at the beginning, I said I'm looking for betas. Each one is p dimensional. I'm looking for k of them. So in fact, that beta hat is essentially approximating these guys. I mean, not approximating, yeah, approximating a model. Okay. It's essentially a substitute for these. Right? Once you get these betas are essentially the same betas as here. Okay. And why is that? You can actually, so for that, let me give you a slightly different point of view. If you actually if you don't like this version of the problem, think of a slightly different version, which is equivalent to this. Actually, you can show that it's equivalent, which is as follows. You have y's which are, there are k columns here, right? There are k columns here. Just ignore, for the first time, just ignore the kth column. Just think of the first column, y first column, okay? And regress with data x, okay? That will give you some beta 1, okay? That will give you some beta hat 1, right? That's a one-dimensional. You have, you're just looking at one y vector, and you have the x matrix. You know how to do linear regression. And similarly, you do same thing with y2, regress with x data matrix. You'll get beta hat 2, and so on. So these betas, if you stack them together, these are going to be p-dimensional. You stack them next to each other, okay? There will be k such betas. That's the same beta as this. So you can either do gigantic regression with k output variables and p input variables, or you can do k such regressions where output variables is one-dimensional and input variables are p-dimensional, and stack these betas as columns. You'll get the same beta, okay? And these betas are essentially the betas that I was talking about earlier, okay? And why is that? Because y's are, remember what was the first column of y? It's basically saying, it basically looks like this, right? It looks like somewhere it's ones, somewhere it's zeros, somewhere it's ones, right? It's basically saying, okay, for this observation, the first observation, the label is 1. For the next observation, the label is not 1, so it's 0. For so many observations, maybe the label is not 1. For maybe some other observation, label is 1, again it's 1. So y, each y just looks like this. It's one hot encoded, one column of the one hot encoding matrix, right? This is like this is like the outcome of this. It's basically saying what is the probability of g is equal to 1 given x is equal to x, right? So you are just looking at the realization of that. This is the probability. If you flip the coin, it will either be 0 or 1. With some probability it's actually equal to L, with some probability it's not equal to L, right? And it's not equal to L, you will see a bunch of zeros, and it's equal to L, you will see 1, right? So there is a relation between this assumption and the betas that we kind of computed. Okay. So this is how you use linear regression for classification. There's nothing, I mean, if you, you basically have to create a one-hot encoding matrix, do regression, either this one or individual ones. Those betas essentially, those betas are what you want to find. And then how do you actually classify? Given a test point x0, okay. So given x0, find the maximum over L is equal to 1 to k of beta hat L transpose k. In the sense, you got these k betas, find beta transpose x, right? You have k such numbers, and you find, to get the class, just find which beta transpose x was the highest, and that index you just call it the label. Okay. Argmax, I guess. Argmax just means the index which maximizes one of these k numbers. So there will be some index, and that will be your class label. That's it. So this is your classification using linear regression. Has this method been covered somewhere else? No. Okay. Who are so out of people present here? Who's not taking 572? Just one. Okay. So, I mean, so for others who are taking 572 or have taken 572, have you seen linear regression? Have you seen classification using linear regression before? So it's fine. What about people who are taking it now? Have you seen it? Okay. But you have seen some classification techniques. Okay. Okay, so 2 class or k class.
This form is totally new.
Yeah.
Okay,
So
okay.
if there are two classes, cat and dog, then dog is included more
Yeah, but that we saw, right? So that was the base classifier. Remember in second lecture we said in the true distribution for a given point, if dogs, the probability of dog is more than probability of cat, then that would be the best class to predict, right? For a given point, given feature vector, it could be there's a small probability that's a dog, there's some other probability there's a cat. But whichever probability is higher, that's the class that you need to predict. That's the base classifier. That's the best thing you can do if you have the distribution between G and X. But you don't. You only have data. And so you're going to make some assumption, linear assumption in this case, and then use data to fit these parameters because of linear assumption. What's the time? Okay. Now, okay, so I want to give one more. So, okay, the reason why you probably did not see classification using linear regression is because of an issue with this model, which is going to be as follows. It's called class masking. Okay, and what is the issue? I'm going to illustrate using an example. So let's say we have three classes. Okay. Red, blue, and green. I think in the notes maybe there's something else, but don't worry about it. Let's say we only have one-dimensional classification problem. So there's a bunch of red points here. I'm going to call them x's. Bunch of blue points here. I'm going to draw them as circles. Bunch of green points here, which I'm going to draw it as squares. Okay. Right. So just three sets of points, and in this case, I've nicely put them, in three separate clusters. So you can see that. The way to classify it is to have something over here and something over here. So anything less than some threshold is, red class. Something between is supposed to be red and, blue class, and anything greater than this threshold in terms of the value. So our x is just x1. There's only one feature. Okay. This is x1. There's no x2. Okay. So it's only like if x1 happens to be greater than some threshold, let's call it tau 2 or tau 1, whatever, some thresholds. If it's greater than tau 2, then just classify it as green class. That's it.
So it's always going to be that nicely separated?
No, I'm giving an example. For this data set, if you want to do classification, this is the best. This by eyeballing, this is the classifier. You can one-dimensional classifiers are just threshold classifiers. You just have to look at intervals, right? Because there's only data on one interval on the real line. So your classifier is always going to be, if you are between x and y, just classify something. If you're between some other thing and some other thing, classify something. For this, I'm going to say that I'm going to show why linear regression fails. This is just an example. This is not true. Linear regression need not fail all the time. It's just going to fail for this one, which is that, like if I'm going to do linear regression, I'm looking for a linear function of x. So I'm trying to look for y is equal to some constant times x. Right? Linear function. So I can draw the linear function f of the y is equal to, so for linear regression what is going to be? It's going to be y is equal to some beta times x1. Here there's only one. Actually it's going to be beta times x1 plus beta naught, some offset as well. So you will see that the linear function will be such that it may be like this. So I'm going to draw a linear function. So I said so for linear regression we have to do three regression problems, right? Essentially we're getting beta one set of betas for this, one set of betas for this, one set of betas for this. Right? So let's say this is the line for this guy. Clearly this the y is higher than for these two guys. Here the y's are 1. Remember in the data, the y's are 1. Here for these data points y's are 0s. So you can imagine that since here it's 1, you will fit a line like that. And similarly, you'll see that for the x's, you'll have a line like this. Where is the symmetric one? Something like this. And for this class, B class, unfortunately, because it's in between these two, here there will be 1s, and here it's 0s, and here it's 0s, the y column, remember, in the training data. You can't tilt the line either way. Okay, so you'll have a line which is horizontal. Okay, if you just fit the data, fit the three regression problems that you'll get, you'll have a line like this. Okay, this is it. This is your data fit. Okay, there's some. Is this clear visually what I'm doing? So linear regression. So forget about 2 lines. So for one line, for one problem you have 1 line. Sorry, one class you have 1 line. So you have 3 lines. So why are the lines tilted like this? Are you able to reason? Right. For this class there will be corresponding yi's. Observations will be 1s. For these data points, the corresponding observations in that column, that y column, will be 0s, and here will be 0s. So you can see how to fit a line when there are 1s here and 0s here. Right? 2-dimensional plot. There are 1s here, 0s here, then this is roughly the line you get. Right? Okay, just to kind of, I know this is for those who didn't get it. So let's say, I have a bunch of points here, and I have a bunch of points here. Okay, this is my one of the regression problem. The third regression problem essentially is saying my x comma yi pair is x is something, y is 0, x is something, y is 0, x is something, y is 0. Here x is something, y is 1, x is something, y is 1. So here if you fit a line, remember in R and stuff you fit a line, right? So you'll fit a line like this. That's a line. And similarly you have this symmetric line. Like you'll have a problem which will have dots here, and so that's this one. There'll be a line like this. And similarly,
when we have separation like this, like some with y zeros and then some with y is equals to 1, then
Yeah.
we go like this instead of.
no, but you're fitting a linear line, right? Linear model. What will this is the fit for this data. If you do linear regression, if you do LM, this is what you get, right? It's a you have xi yi pairs. You just fit a line. This is the best line. Is there any confusion?
I'm not getting like why we have 3 lines.
Because we did 3. I think I just showed you that if you have 3 classes, k is 3, then either you do whether your data has 3 columns, whether you do a 3-column versus in this case 1-column regression, or you do 3 different regressions. I just showed you here, right? You do 3 different regressions. You just take the first column with data, do a regression, you get a beta vector. Second column with data, do regression, you get a beta vector, and so on. So you'll have 3 regressions. And so this is it. So with this estimated models, 3 models, you can see why class masking happens. I said my classifier is going to be the max of these three lines at any region. And you can see that in this region, the max of these 3 lines is this line. Fine. That's the red part. It's correct classifying correctly. In this region, the max of these 3 lines is the green one. So that's fine. That's correctly fitting that thing. But in this region, the max of these 3 lines is never this horizontal line. It's either this side or that side. Okay? And so you're never picking the class which is corresponding to this line. Okay? I mean, of course, if this line was higher over here or something, you would see that you can pick that. But this is just an example data set where you can ensure that the line is never being beaten. This line is never beating these 2 lines, essentially. And so you'll never pick the green class. Sorry, you'll never pick the blue class. Okay. So that's called class masking.
Just to clarify, so this is the issue when we
Use linear regression
when we use linear regression on
for classification. You may not know. So this in 1 dimension, you can eyeball this and say that there is class masking. If it's going to be a 10 class problem with 100 variables, then you cannot really eyeball and say which class got masked by which other class. Okay?
Is there a way to test for that ahead of time?
No, that's the thing. That's why it's an issue. I mean, maybe you can figure it out. I don't know. At the moment, I think there is no way to test this ahead of time. Okay. So I'm going to introduce 2 models. One is called linear discriminant analysis, I think. Yeah. And the second is called logistic regression. And these 2 don't have class masking issue. And I'm going to define how they approximate. So both of them will do something with, just like linear regression did something with probability of G is equal to L given X is equal to X. These 2 also will do something with these quantities. Okay. In fact, they'll do something with the ratio of probability of G is equal to L given X is equal to X divided by G is equal to the last class given X is equal to X. Okay, they'll try to approximate this as actually log of this as actually linear beta of L transpose X. Okay, both of these try to do something like this. Okay, but I'll describe what this is. This assumption right after a break. Okay. Yeah. Any questions? You can come. Yeah.
So, I mean, I get what the class system is because you have three regressions, you have lines.
Yeah.
So you have three linear lines. So how is it that the linear regression fails in this case?
Because this is the best class in your prediction. You're always going to take you're going to look at what the value of the regression is. So for any new point, let's say I give a point here, you see that this value, the estimated value for this line is higher, and so because this line fits the green class, then you're going to classify it as green. Right? You're just looking at you're just looking at once you have fit these three lines, you're just looking at for any new point, your classification is going to be which line is higher on the y. So this line is higher, it's going to be green class. And so this class is getting this line, if it was higher here, then in this region at least, you could have predicted blue, but because it's over here, you cannot predict blue ever. So the blue class is getting masked completely. That's what I mean.
Oh, okay. So
In your diagram you actually drew it as you did your triangle there. I didn't give a triangle there because otherwise there's no class.
yeah, I made mine very even but also if it's like blue, then only the other regression line can't account for it and it has to be on the other line, so it masks it.
Yeah. If this line was higher, then it's not masked.
Yeah, but since it's lower.
It's at the same place or lower, it's going to get masked.
And argmax is just you're finding the x that maximizes beta.
Not X. Arg means the index that maximizes beta transpose X.
Okay.
So we are maximizing our L values, right? K values. We have K classes, so K linear values. So I'll have one number per K, per L, the K such L. Right? These are, so basically for example think of this point, I have three numbers, 1, 2 and 3. So those are the three numbers here. I'm just asking, give me the index of the number which is the maximum. So for this is the maximum. So that's the third index, which is 3. Index of the maximum. Index of the maximum, yeah. Index is always going to be the class, which is going to be one of the K values. Yeah, argmax just means which of the K values, so which of the K values was the one which led to the maximum. Instead of, if you did not have R, it would say what is the maximum value. If it says argmax, it tells me what K, so what L led to the maximum value.
Oh, okay. Okay.
Yes, sir.
For lasso and rates, I was just wondering how will alpha affect the shape of these graphs? Like, will it just
What is alpha? Lambda.
Lambda, sorry.
The shape of these graphs.
Yeah, these graphs.
Yeah, so the graph will become, so I do something like this, right, for lasso. This is for, so lasso is basically beta j is assigned to t, sum over j. Okay. This t happens to be inversely proportional to lambda. That lambda, the coefficient.
Yeah.
Okay. If you increase lambda, okay, t will be smaller, which means that you are preferring smaller and smaller sets. If you increase lambda, you're gonna get, and you can see when lambda is really, really large, you basically you're asking, I don't want to pick anything which has any non-zero number here.
It's almost as if this mean square error.
No. When lambda is 0, it's mean square. When you make lambda 0, then t is infinity, so this constraint doesn't exist.
Yeah.
So you're saying I'm going to look at a region which is like this, and which is like saying anything is valid.
Okay.
So it's just original least squares. Yeah.
This is 2D, so it's easy to visualize the beta graph.
Yeah.
How is it going to be?
You can't visualize this. This is just for intuition of how this constraint works.
So for, let's say in 3D, is it still going to be having
3D,
edges?
Yeah. for every corner there's going to be, in 3 dimensions it's going to be like, there's going to be some surface like this, some surface like this, right? It's going to be, I don't know how to draw this.
Okay, so basically it's gonna have edges.
Yeah, I mean it's going to have, it's going to be like, every projection will be like this. So on this plane it's going to be like this,
Got it.
right? On this plane also there's going to be another thing like this.
Okay.
On the other plane also there's 3 such lines.
Okay.
So because there are many corners, right? So the number of corners increases as, so in 2D the number of corners is 2 to the power 2, 4 corners.
Okay.
In D dimension it's going to be 2 to the power D. Okay. In let's say 3 dimensions it's 8 corners, 2 to the power 3.
So more
So
chances of having.
yeah, because there are too many corners, you can probably hit beta 0 for appropriate choices of T. I mean appropriate choices of lambda. Okay, so let's resume. Okay, so classification. We looked at how linear regression can be used for linear regression can be used for classification. I didn't mention one thing, but linear regression based classification solution gives you linear decision boundaries. Okay, and you saw that. I mean, here you cannot see linear decision boundaries because you can see the decision boundary for this classifier is just this. It's saying here, if it's to the left of this, then classify everything as red. To the right of this, we classify everything as green. It's not really linear because in this degenerate case it's a point. But if you look at 2 dimensions, you will see that there is going to be a linear boundary. Okay. To the left of a line, classify something. To the right of a line, classify something else. Okay. And that's one of the common features for. I think I used A here. This common feature for linear regression based classification and LDA and logistic regression. Okay. So what is LDA? So actually, let me just call it linear here. Okay. So what does linear discriminant analysis do? So linear discriminant analysis is I guess the first word linear just means you're going to work with just linear functions of x. That's fine. Discriminant is just a placeholder. It's a name for some of these intermediate functions that you will see in while defining the classifier. Okay. They are essentially, so in this case the discriminant function would be this. This is a discriminant function because it's discriminating between classes. There's really not much deeper notion to what discriminant analysis this means. Okay. Okay. So an LDA is basically a model which is gonna assume something about so it's a generative model. Okay. Is a generative model, maybe I should write is a generative model. So again, lot of another name here. All it means is that LDA makes an assumption about the joint distribution between G and X. That's what a generative model means. It's going to make an assumption between the joint distribution of G and X. It's a so contrast this with generative model assumes. Generative model assumes P of G comma X as something. In contrast to that, all the models that we've seen so far are discriminative models. Okay. Assumes something about the probability of G given X, or basically P of Y given X. If you remember, linear regression is only assuming something about the conditional expectation of Y given X, which is only a function of Y, P of G given X. Sorry, P of Y given X. So that's called a discriminative model. Discriminative just means thinking only in terms of conditional distributions. We don't care about. So what's the difference between this and this? So the difference between this and this is that this is assuming something more. It's actually assuming the distribution of x's as well. Okay. In other words, just look at this identity. P of G X is actually equal to P of G given X times P of X. This is just the definition of a joint distribution is nothing but a conditional distribution times the marginal distribution. This identity holds. Okay, this is just a factorization of any joint distribution. You can factorize the joint distribution as a conditional times the marginal. Okay. So what I'm saying is, a generative model assumes something about this and this because it's assuming something about the joint distribution. A discriminative model only focuses on this guy. Doesn't care what this distribution is. Doesn't assume anything about. Okay. Doesn't assume anything about this. Only makes an assumption on this. That's the difference. And let's see what the generative model is. It's going to be as follows. So it's going to assume that the probability of X given G is equal to, let's say, the nth class is equal to, in fact, it's going to assume this to be equal to a normal distribution with a mean nu L and variance sigma. Okay, so that's what LDA assumes the conditional probability of X given G is equal to L is normally distributed. Okay. I mean, I'll complete the story of the joint distribution first, but let me just say what the what this is.
What is the symbol on the right hand side?
Mu L. Since it's class L, the normal distribution should have a mean, so I'm just calling it mu subscript L, and it also has a variance. X is could be p-dimensional, so in p dimensions, instead of sigma square, I'm just writing it as sigma, capital sigma. Okay, it's a matrix which is p cross p dimensional. It's a multidimensional Gaussian. One-dimensional Gaussian, you remember, it was just 1 by square root 2 pi sigma exponent of x minus mu square divided by 2 sigma square. So similarly, in multi-dimension, it's going to be 1 by square root 2 pi instead of sigma. There is this determinant of this guy inverse. I'm not sure there's an inverse determinant. It's e power x transpose sigma x. Actually, let me not write it because there's some subtraction of mu and all that, and there's no space there. Okay, let me write it here actually. Times exponent of minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, it's just a. I mean, it just reduces to this. Like if sigma is one-dimensional, then sigma's, the one entry in sigma is going to be sigma square, and there's an inverse here, so 1 by sigma square. So minus 1/2 sigma square is there, and since this is gone, and x is one-dimensional, so this transposes this is just going to be x minus mu square. Okay. And determinant of sigma is just there's only one entry, so it's just sigma g square root of determinant. Anyway, it doesn't matter, so let me not put x here, times. Yes. So that's the normal distribution, that's the assumption that we're making. Okay. So I haven't completed the picture because I've just said, okay, the conditional distribution of x given the class is this. We'll also assume that the probability of the class itself, G is equal to L, is something. Let's call this pi L. Okay, some number. Okay, classes are only k classes, so this is a marginal distribution of being in the L class is just this. Okay? This is just saying P of G of L is equal to pi L, P of G is equal to K is pi K. Maybe it may sum to 1 because any distribution function this needs to sum to 1. Okay. So given just these two, I can say something about probability of G given G is equal to little k given x is equal to x. Why is that? I can use the definition of conditional distribution. So it's just our base rule, if you have heard of this before. It's just the probability of x equal to x given G is equal to little k times pi little k divided by probability of x is equal to x. Okay, this is just base rule. Or in general, so this product, right, is equal to p of x is equal to x, comma g is equal to k, and this product, this times this, is also probability of g is equal to k, comma x is equal to x. That's just so if you bring this to the left hand side, the left hand side is the joint distribution between g taking specific values of k and little x, and right hand side is also a joint distribution between x and g taking a specific value of x and k. Same thing. The base rule. Okay. The denominator, actually you can write it as let's not worry about expanding the denominator. So this is fine. Now, so I have defined one conditional distribution, one marginal distribution, and I just derived another conditional distribution from those two, right? Now I'm gonna make an assumption, which is that the log of the probability of G is equal to K. Actually, yeah, I don't know assumptions needed actually. So I'm just gonna evaluate what is this log of probability of G is equal to K. Log of the probability of G is equal to, let's say, little k, given x is equal to little x, divided by the probability of G is equal to L given x is equal to little x. Okay, for some two classes. Okay. And what's the reasoning for doing that? I need to make an assumption about something to do with the class conditional probability. In the sense, something to do with this type of thing. Like linear regression made an assumption that G of probability of taking some specific class given the data is linear. Linear regression did something like that. Here we want to say, what assumption can we make about this guy? Okay, we already made an assumption about this guy, right? We said probability of x equal to x, which is given G is equal to a particular class, is normally distributed. We already made that assumption, right? So we have made an assumption on this one. We have made an assumption on this one, right? That's basically telling us the assumption about the John distribution, right? Because this times this is actually the John distribution of taking two values, x is equal to x and k is equal to k. I made an assumption on the John distribution already. Right? Now, the reason why I took a ratio is so as to kind of get rid of this. Okay, I mean, because I know the John distribution, I can also compute this, but it's going to look ugly. So let me actually kind of get rid of that by taking a ratio. Okay, because this doesn't depend on L or K. So if I take a ratio, I will get rid of the denominator. The log is because, we'll see the log's effect, because log is because this happens, because I'm assuming this to be normal, there's an e to the power something term, and make a log so that I don't have to, I can cancel out the e to the power something, because in the normal distribution there's an e to the power, that's all. So you'll see that this is equal to the log of pi k divided by pi L, okay, and there's a very unwieldy expression here, 1/2 mu k, mu little k plus mu little l transpose sigma inverse mu little k minus mu little l. Don't worry about writing this, it's kind of not very critical. I'm just writing it because I just want to kind of focus on a couple of terms. X transpose sigma inverse mu k minus mu l. Okay, and that you can just just substitute this definition with mu k mu l into this, right? This anyway, ratio, take the ratio, this one is gone. This pi k remains, and that's why you have a pi k times pi l. If you have a log, things add up, right? That's why there's if something is multiplying, it just becomes an additive term here if you take a log. And because there's an e to the power something and log, so this whole thing comes down, but it turns, because there are two terms here, you get a mu k plus mu l, mu k minus mu l, and something like this. Okay. Don't worry about it, that computation is not very critical. What is interesting is that this function, you can see that this is actually linear in x. Is linear in x. See this, there is no x here, first of all. There is no x here. There's one x here. So this x transpose something, and this thing has to be, just for consistency, this whole thing has to be p cross 1. Because x is p cross 1, the x transpose is 1 cross p. So this whole thing has to be p cross 1. What I'm saying is, there are some constants, plus x transpose, another constant. Constant as in something is, which is about our assumption, about the means and the covariance, and this log ratio is linear. Okay, turns out to be linear. It's just a consequence of us making an assumption that the conditional probability of x given at the class label is normally distributed. Normally distributed. Because we made this assumption, we get that the log ratios are linear. Okay. That's a consequence of this assumption. We did not need this property explicitly, but it's useful to kind of. This will tie us this will let us understand logistic regression. Okay. Okay, so this is linear. This implies that the decision boundary is also linear. Why is that the case? Because remember, what was the decision boundary? Decision boundary is where you don't know which class you belong to, whether you're on the left side or whether you're right side. So when does that happen? When it precisely happens when the probability of G is equal to some class L given x is equal to x is equal to probability of G is equal to k given x is equal to x for some other class. So let's say it happens that at given data point, the probability that it belongs to one class is the same as the probability it belongs to another class. Then this is the probability that you're matching. Okay. If this is true, then the right hand side of this log, the right hand side term, log of two things which are equal, log 1 is 0. Okay. And 0 equal to some function, some linear function of x is a line, okay, in 2 dimensions. In higher dimensions, it's a plane. What I'm saying is the decision boundary is linear because decision boundary is exactly when this happens for a couple of classes. Let's say pick 2 classes. The decision boundary between 2 classes is this precisely. If this is true, then the right hand side is 0, which means that the left hand side is the equation because left hand side is a linear function of x equal to 0 is an equation of a line or a plane in higher dimensions. So the decision boundary is linear. So that's why it's called linear discriminant analysis. And that's fine. That's another consequence of us choosing the normal assumption. But what is the classifier itself? Like, how am I going to classify? It's going to be based on, again, what is called the, I'm going to take a max, argmax of L is equal to 1 to capital K of something called discriminant functions. Okay. What are discriminant functions? These are just going to be the discriminant function is nothing but it's going to be just this, because the discriminant function is just going to be related to this. Okay, the class probability of G is equal to K given x is equal to x. And why is that? Let's just again recall that the best classifier was just this, right? It was just argmax of L is equal to 1 to capital K of probability of G is equal to L given x is equal to x. This was the base classifier. If we knew the Joule distribution between G and x. Okay. And here I'm saying we're gonna, instead of this we have something else, and that's just gonna be, we had assumed this conditional probability of G is equal to L given x is equal to x as that, because of normality we had this expression here, this expression. Okay. And because this term appears in every discriminant function, let's ignore it. Okay. And taking a log of this doesn't change anything, because log is these numbers are generally have to be positive. These are probabilities. And so log of positive numbers doesn't change. Transforms all numbers in the same way. So log doesn't impact doesn't change the max. Okay. If x1 is greater than x2 and both are positive, then log of x1 is going to be greater than x2. So log of x1 is going to be greater than log of x2. Okay. So log doesn't change anything. So we are just gonna. So discriminant function is just essentially the log of that normal thing, and so where delta L of x is just the log of that, which is x transpose sigma inverse mu k minus 1/2 mu k transpose sigma inverse mu k plus log of pi. Okay, I think I made a mistake. Let's call it okay, and don't worry too much about why this looks like this. This is just a log of the normal distribution function. there was supposed to be an x minus mu L transpose sigma inverse x minus mu L that they just expanded out. Okay. Otherwise, there was a multiplier of log L, multiplier of pi L, that's why there is a plus log L, and the first two terms are essentially the log of the log of the normal distribution of the numerator. Okay. So to do a classification with LDA, all you need is somehow, if you can estimate sigma from data, if you can estimate mu L from data for every class, let's say there are 3 classes, then there will be 3 different mu's, and there's going to be a common sigma in this model. Okay. Once you estimate these guys, you can compute this for any mu L, compute, let's say there are 3 classes, 3 such numbers, and whichever class is the highest, that's your class prediction. That's it. Any questions about LDA? Other than knowing how to estimate sigma. So just like in other models, we had a very nice expression for beta hat. Here we have to find expression for sigma hat and mu hat L and maybe pi hat L. Okay, we need to know this, right? We have to use the data to estimate these guys. Okay, and this is not very estimating these doesn't require. I mean, you can do it in a very formal way, but the intuitive way works, which is that, let's say pi hat of L. What is that? Pi L is the class. Pi L is saying what is the probability that the class is equal to L, irrespective of my data. I mean, don't give me any data point. I'm just asking what is the probability of my class is equal to L. So you just look at your data. What is the proportion of data points which have classes equal to L divided by the whole data set, divided by the number of points in my data set. So it's basically saying count is basically number of points in my data set with class is equal to L divided by n. N is my data set size. Just look at the proportion of observations which have class L divided by the number of points, number of data set is my estimate for pi L. Okay. Now what's my estimate for nu L? Nu L is saying look at the L, look at those data points where L is the class in your training data. There will be corresponding x's. Take their average. That's it. That's the mean. Mean of the x's of the. So it's basically saying sum over all the i's in data set such that the corresponding gi is equal to L. Basically look at only those rows where the class is actually L. And then take their average. So some, what is this, xi. This is not the average, so I have to divide it by 1 by, let's say the numerator is NL. So let's say NL. Let's say this is NL. Just the count of the number of classes, number of points which have class L. Okay. Sigma hat. Now once you know mu hat, sigma hat is just going to be, the usual definition of variance is going to be 1 by, okay, let me just do it this way. For each class L, you can compute this, right? 1 by NL of xi minus mu hat L transpose this is going to be 1 by NL xi minus mu hat L transpose. What I'm saying is, so let's not worry about how this comes. Looks too close to NL. Let me just delete this. Let's not worry about how. So this is an estimator of variance. But this is only an estimator where I'm saying use the L class's mean. So xi should also be L class's xi's. I'm dividing by the, actually there's a summation missing. Okay. Oh, summation looks like sigma. Okay, it's crazy. Let me just call it sum. Sum these guys. Anyway, what I'm saying is there is a closed form expression for sigma as well. That's not very important. What I'm saying is there are only 3 parameters to figure out in LDA, these 3. I mean, there are going to be, not 3 parameters, sorry. There's going to be k parameters here, k p-dimensional vectors, There's only k numbers for k classes and one sigma matrix which is p cross p. Okay, those are the number of parameters here. Okay, and estimating them is not difficult. I mean, these guys are fine. This guy is also just a variance of your data, so you can compute the variance of your data. It's just multidimensional, speed dimensional. So I wrote a formula which, let me explicitly write the whole formula so that people are not confused. Okay, this is the formula. So 1 by sum over L is equal to 1 to k, 1 by NL, sum over I such that gi is equal to L. So all the data points for which the class label is L of xi minus mu hat L, xi minus mu hat L transpose. Yeah. Okay, there's one more thing. I'm just saying, okay, so this term is the class specific variance, database, what is it? Empirical variance or an estimate of this covariance matrix. I'm just averaging over all classes because this doesn't depend on any class. Okay, so this is the formula, so you can trust this. Actually, let me just scratch it. That's it. Once you get these three estimates, you have this discriminant function. Just do the argmax, and you're done with LDA. And LDA has these properties that it's a linear in X. Log probability ratios are linear in X, and the decision boundary is linear. Okay? And it's making an assumption about that the conditional probability of X given class is normally distributed. Okay? And the next model. So a related model is B. B. I guess B is the same thing. So something called QDA. Okay, quadratic discriminant analysis, and it's basically the same. So the why it's called quadratic is because it's gonna assume, it's gonna lead to quadratic decision boundaries, as in things which look like parabolas. So maybe if there are 2 points here, I mean there's two classes here, the decision boundary will look like this, okay, instead of linear. And what is the change from LDA? The change is going to be that you're going to assume that the probability of X equal to little x, given, let's say, class G is equal to class, the label for G is L, is equal to normal, is also normally distributed with some mean mu L, and a covariance matrix which is dependent on L. Okay. There's the difference between quadratic discriminant analysis and linear discriminant analysis is that there is a subscript L, in the sense that there's a class specific covariance that I should compute. That's the only difference. And as a consequence, the delta L of X becomes quadratic. Okay. Quadratic. So this is assumption. Consequences. And decision boundary is quadratic. And the way you can see that this decision boundary becomes quadratic is again the same thing. You just look at the for linear guy, you looked at this ratio, right? And again, this denominator cancels if you look at the ratio, except that this guy happens to have different sigma L's. Okay, so for the K guy there will be sigma subscript K, which is the covariance matrix, and for the Lth For the nth financial probability, there's going to be a sigma subscript L which comes into the picture. And so those two don't just there's a single sigma which comes here. In the other case, there's going to be, because you cannot cancel out because there's subscript L for both subscript L and subscript K for the sigmas. This function is not just linear. Here it's linear. In the quadratic discriminant analysis, this function is going to be quadratic in X. Okay? It also depends on X transpose sigma Lx and X transpose sigma Kx. So it depends on a quadratic function of X.
Right after the sigma, when there's point, what is that symbol there, right between mu minus?
Mu K minus mu L.
Between the sigma and the parenthesis, what is that? It looks like a -1 or
Yeah, sigma inverse. It's the inverse of a matrix. Yeah. And these are mu's. And these are pi's. Yeah. So everywhere it's basically sigma inverse. This is in the definition of normal distribution, there's a sigma inverse here. Okay. So the decision boundary is quadratic. So what does this bias us? If in reality the data set is such that linear decision boundaries don't make sense, then quadratic discriminant analysis can capture curved decision boundaries. That's the idea. And that's it. That's the slide change. Okay, in the notes I think I gave a different estimator, so I'm thinking, okay, this ratio is not needed. I mean, so both estimators are fine. What I wrote earlier, but let me just be consistent with what I wrote in the notes. I mean, this is basically saying there are going to be total there's going to be total n terms here because class specific number NL. And there's going to be k such tags, so this total is n terms, and there's a minus k there for some correction. Don't worry about it. Yeah, it's not very important what that looks like. It's an estimator of covariance. So, okay, so QDA is just that. Any questions about LDA and QDA? This is almost a last lecture where we're going to kind of deal with linear models. Then we're going to give up linear models. So we're trying to stick with linearity because even once you introduce interactions, I think I gave this reason earlier as well. So linearity is really not such a strong restriction because you can think of quadratic terms and so on, and then you'll have still linear coefficients, right? You can have a polynomial. Okay, you don't think of a polynomial as linear, but then the coefficients is what are just linear for us. Okay, so you can have. So what do I mean by that is because if you had a linear model which was just beta transpose x, you can also have a model which is like let's say beta 1 x x1 plus beta 2 x2. Then you can also have a model which is beta transpose x, I guess beta tilde, where x is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x1 square plus beta 4 log x1 x2, things like that. So in a sense you can always transform your feature vectors and you can look at much richer you're going to increase the dimensionality of your input space, input variables, that's all, and still be linear. Linearity just means the linearity with coefficients, okay, not with respect to x's. Yeah. Sounds cross-validation. But I mean, there are different sets of assumptions that they're making, right? So if the assumption is correct, for example, the LDA, if the assumption is correct, that in general, that per class, the probability of probability of x per class is actually normal, then using an LDA will give you will give you the right answer anyway, will give you the base optimal classifier, but it will also require less data. So if you had 100, if you had 1,000 data points, and the data actually corresponding to the assumptions made by LDA, then 1,000 data points, the model that you get with assuming an LDA model would be a much better model than 1,000 data points and doing, let's say, the linear regression based classification or logistic regression that I'm going to talk about next. So if assumptions match the unknown ground truth, which is not something that you can verify, then the models shine. But in general, because we don't know what the ground truth is, we have to do cross validation. Okay, so third model is logistic regression. And this says, okay, now we're going to come back to the discriminative modeling world, where we don't really want to think about joint distributions anymore. And logistic regression is going to assume the following. It's going to say, okay, let me not think of joint distribution at all. Let me just think of the conditional distribution of G is which is this. In regression, in classification, always the conditional distribution that we care about is this. We're going to assume that the probability of G is equal to L, and the probability of G is equal to, let's fix the last class to be something. So let's say capital K, X is equal to X. The log of the probability of this, this probability ratio is linear. Okay, beta vector L transpose X. Okay, I'm just going to assume that to be linear. It's a weird assumption to make. I'm not making an assumption about a specific conditional probability. I'm saying that a conditional probability divided by another conditional probability, the log of that is linear. Okay? It's an assumption for logistic regression. Right? Again, just think of all the assumptions that you've seen. Linear regression, the assumption is linear regression. For regression, the assumption is that conditional expectation of y is equal to x is linear. Right? For KNN, there was an assumption about the same thing. For LDA, there was an assumption about this ratio. I mean, not the ratio, but the probability of x given G was normal. Here, the assumption is log of the conditional probability ratios is linear. Okay. And what's the motivation for thinking of this? Is because when you made the normality assumption, it turned out that the log of the probability of this conditional probability ratios was linear in LDA case. So in LDA, you made a normality assumption, and then you check that the log of the probability ratio is actually linear in X. Linear in X. Okay, we saw that, right? Couple of pages above. Where is it? Yeah, here. This log probability ratio, because we assume normality, there was this log and the exponent of the normal distribution cancelled out, and there was basically it's just linear function of X. Okay, with some other things which don't depend on X. Okay. Now, logistic regression is saying, okay, since you are anyway assuming that, let me forget about normality and all that. Let me directly assume that the ratio of the conditional probability distributions is linear. Okay, that's the assumption in logistic regression. Okay. If you assume this, I mean, you can see that because I have to assume ratios of things, I mean, I can keep changing L at the top from 1 to, let's say, K minus 1, because if I set K, then anyway the right answer is 1 and 0 doesn't make sense. So I can make this true, I mean, I can do this, make this assumption for L is equal to 1 to capital K minus 1. Okay. If I do that, this assumption also, implies the following, that the probability of G is equal to L given X is equal to X is equal to e to the power beta L transpose X divided by 1 plus summation over little k is equal to 1 to capital K minus 1 of e to the power beta little k transpose X. Okay. I mean, given these, you can just take, instead of log, you just put the log over here. I mean, take the exponent on both sides, then you'll have a ratio. So you get a e to the power beta subscript L transpose x, that's something like this. And you have to somehow figure out what this is. This turns out to be equal to 1 by 1 plus this thing. Okay. Why is that? Because the conditional probability solves need to sum to 1. Like for a given x, the sum over all L should be equal to 1, and that's why you'll get a ratio like this. So this should be familiar to you guys. This looks like a I don't know if you've seen this, but it looks like what is called the softmax, or if you've not seen softmax, don't worry about it. And why is it called logistic regression? Because this log ratios is called a logit transformation. Okay, the logit is linear, or this log transformation of the ratios is called logit transformation, and that's linear, so that's why it's called logistic. The first part, regression, is I don't know what the misnomer is. It's for classification. Okay. And again, what is the classification rule? Once somehow you could figure out these beta L's, the k minus 1 such guys, then all you need to do is again the same thing. It's always argmax of L is equal to 1 to k minus 1. Argmax L is equal to 1 to k of p of g is equal to L given x is equal to x. In the sense you find the parameters betas. You know the right hand side, just substitute that, compute that for every L, right? For every L there's this ratio, and take the one with the maximum. I mean, this is the same. I mean, what I wrote here is just the base optimal thing, but what I'm saying is here, since we're assuming something like this, you substitute the one on the right hand side. Okay. Right. Any questions about logistic regression? So this you must have seen in the other class. So let's see what is the inconsistency between what you have seen in the other class and here. Do you remember what you learned? So did you look at 2-class logistic regression or k-class logistic regression? Huh? Oh, it has not been taught. Logistic regression has not been taught yet. Okay. 2. Okay. So what we are looking at is directly k-class logistic regression. Okay. What is what?
I mean, in any other discussion, logistic regression, it's always log odds is always a key term that is thrown around.
Yeah, we did. This was a log odds. Log odds. Log of odds. I don't know whether it's called log odds, but we think in terms of joint distribution, conditional distribution. I mean, this is the object that we've been playing around for classification since second lecture where we introduced this. And the assumption in logistic regression is that the ratio log of the ratios is linear. That's it. It's just a unified view of all these models, all these linear models. So you just want to kind of remember what is the assumption being made for all of these linear models, right? And it's tied down to the statistical basis, right? It's not just out of the hat that if they said, okay, let's just assume something like this and it works. So, but some of you said you did look at logistic regression this week or something. Who? Okay, Sid's class. Who's taking Sid's class? No, I'm just asking so that you can reconcile, right? I mean, can't look at logistic regression of 576 is different from logistic regression of 575 is different from logistic regression of 572. It cannot be the case. So I just want you to kind of, especially if the same concept is being taught, you kind of should scrutinize and ensure that you have the same understanding of the model, better understanding hopefully. Okay. So definitely, raise questions if you think there's some conceptual leap here. Why is this? Sorry. So the denominator. Why did we choose this? So we just fixed one of the classes. By default, I chose the last class to be the denominator. So I'm saying the probability of every class divided by last class, the log of that is linear. Okay, that's why I've taken only k minus 1 such guys. You can pick any other class. I mean, it doesn't have to be the last class. But I had to kind of somehow assume something about ratios of these conditional probabilities. And so I fixed one of the classes to be the last class. Yeah, any class. I mean, so there's no really notion of which class. There's no order relationship between classes, right? Cat, dog, fox, or is fox, dog, cat, doesn't matter. So fix one of them.
So is it like probabilities of any two classes are
Linear. Yeah. Yeah, the log probability of, I guess this is called log odds ratio, as Scott was pointing out. So is linear. Okay. But it's not true for any two. So we're going to fix one of them, and then everything related to that is going to be linear. So
and it doesn't matter either, like whether probability is more for this class, let's take that.
no, it doesn't matter.
Higher probability.
No, there is no. I mean, so this is an assumption about the unknown conditional distribution between G and X. Okay, you don't know this is an assumption. Yeah, so you don't know this conditional distribution. Right? So in all, like in LDA, you did not know anything about the joint distribution G and X, but you then assume that X given G is a normal distribution. Okay, here you're making a slightly different assumption, saying that I don't know what the joint distribution or the conditional distribution between G and X is, so I'm just going to assume that the ratio is linear. They need not be linear. Okay? They can be arbitrary numbers, right? I mean, arbitrary functions. For every X there has to be a number here, so it's an arbitrary function of X. Why should the ratio of two functions, log of the ratio of two functions be linear? It's not. So whenever I write this, you need to think of this as a function of X. Okay, it's basically, think of the linear regression version of the problem. There it was a function of X which is just linear. So for every X, I'm just making a linear prediction that it was basically beta runs with X for the linear regression version of classification. So this is the function of X, which how do you approximate it depends on which model class you use. In LDA, this is not linear. Neither is this linear in logistic regression. You can see that this is not linear. It's actually e to the power. It's not related to X in a linear way. In LDA also, it's not. This single term by itself is not associated with X in a linear way. So this is not a linear function of X by itself. But the log of the ratio of two functions is assumed to be linear. So it's a relative linearity that's being assumed in LDA and logistic regression.
I guess the folks haven't seen this statistical regression before. I've always found it helpful to actually see the points and draw the S curve on just a simple two-dimensional case to kind of illustrate
What is? But there's no.
Yeah, like earlier when you had the points at 0 or the points up, you drew a line between them, and you could tell that it's
Yeah. You're saying something like X is here and 0 is there, and there'll be a sigmoid type of function like this.
that always helped me understand.
How? Okay, so the thing is, relating this to what we are discussing, this is a vast simplification of what we are doing. Okay? This is not so. Okay, let me actually do the relationship. We have half an hour, so let's now specialize to two classes. So let's say capital K is 2. Okay, so we'll try to understand why this curve makes, why people draw this curve. Let's say K is equal to 2. Then what we can do is, instead of for k is equal to 2, we are saying probability of so there are two classes, right? So G can take two values. G is equal to either G belongs to either 1 or 2, right? So probability of, let's say, G is equal to 1 given x is equal to x is equal to e to the power some beta transpose x. So I'm not writing the subscript here because it's just going to be beta 1, so we don't care about. There's not going to be any beta 2 because one of the classes was always the denominator, and we never had. So there's no beta corresponding to capital K here, right? Remember, there's no beta subscript corresponding to capital K. So capital K is 2 here, so there's no beta corresponding to 2, so there's only one beta corresponding to 1, right? And then the denominator is 1 plus e to the power beta transpose x. Okay. This is it. This is, just the summation and everything, and subscripts all vanish, so you just have this. Okay. So probability of one of the classes is this. The probability of the other class is just 1 minus this, because they need to sum up to 1, right? For any given x, probability of G is equal to 1 given x plus probability of G is equal to 2 given x should be summed to 1, right? So let's not worry about the other class. Now this is so this function is essentially e to the power z divided by 1 plus e to the power z right, where z is equal to beta transpose x, right? I just substituted instead of beta transpose x, I just wrote z. Okay, sure. Now this is also, I can just rewrite it as 1 plus e to the power minus z. Okay. The way you look at it is just take this thing, divide each term here with that e to the power z. So you'll have 1 here and 1 by e to the power z. And so I just wrote it as 1 plus e to the power minus z. Okay. Now this function is it's called a sigmoid function. Okay. It's called sigmoid function. And it looks like this. Okay. It's a function of z. So z. It's gonna go from 0 to 1. So when think of z, let's say z is minus infinity, going all the way to this way. Then e to the power minus when z is minus infinity, it's e to the power infinity, right? Denominator is e to the power infinity, which is essentially infinity. So 1 by something really, really large is 0. Okay, when z is when z is minus infinity, okay, 0. When z is infinity, then this term is 0. It's 1 by 1. That's 1. Okay, so on the y-axis, this is around 0. This is around 1. Okay, and at z is exactly equal to 0. It's 1/2 because e to the power 0 is 1. So 1 by 1 plus 1 is 1/2. Okay. So this is a sigmoid function. This is the logistic curve that we are talking about. Okay. And so it's basically saying, so what we did here is just kind of look at the conditional distribution of one of the classes, because the other class is just 1 minus that, so that's not very over. Given any data point is just essentially a sigmoid function. Okay? Let's assume that even x is one-dimensional, okay, for simplicity. Now, if x is one-dimensional, then it's not beta transpose x, but some constant times x. Right? There's only one term here, so some coefficient times x. X is one-dimensional. So instead of z, you can think of it as a function of, instead of z, you can just think of it as x. So basically, if x is one-dimensional, there are some bunch of points here, bunch of points here. So you're fitting a conditional probability value, which looks like a sigmoid, okay, which looks like a logistic curve. That's all. The conditional probability of class 1 given x's are here is almost 1. Given conditional probability of class 1 given x's are here is almost 0. Something like that. Is that confusing or more clear? I don't know.
So in this case, I know in the past it seemed that trying to figure out where the boundary is can be tricky. Like if you're getting things. In that case, it's simple if the data is more on the line and close to the boundary. In this case, we just pick 1/2 is where we say which class is which class. But going back to your more general case,
Yeah.
How do we get that boundary?
No, it's 1/2 for this guy, but more general case, the complication comes because it's not one-dimensional. Even if it's one-dimensional, it's not 1/2 because it need not be, because z is equal to some coefficient times x. So you need to optimize that coefficient to minimize a certain type of. Remember the type of loss that we had looked at in lecture 2 was this 0-1 loss. There was a matrix where the diagonals were 1 and off diagonals were 0, and only when our prediction was the same as diagonals were zeros and off diagonals were 1. Only when our prediction was off, we had a 1-point loss for our prediction model. Okay, so what I'm saying is it's not true. So what I drew here is only when z is exactly equal to x. Okay, when coefficient is 1. When coefficient is not 1, first of all, this will be shifted and all that. Okay, and first of all, if this is higher dimensional, it's not even, this picture is not appropriate. Okay, I think this is the right picture to stop at. That's like it's something like this. Okay, just stop there. Maybe you can so this is, up to this it's correct, and then you can kind of to build your intuition, you can think of what happens in one dimension when x is one dimension, what happens when x is two dimension, just to get an idea. But these curves are, you will never see them in with your data set anyway, unless once you have built a model, then you compute z's, and then maybe you can look at something like this. Like once you've already figured out a model, okay, in 2-class setting, and then you can, for all your training data, you can multiply this and get some z's. Then you can plot the z's on x-axis and see how the condition, what is the curve that look, how does the curve look like. But that's just for visualization for yourself, I think. Okay. What's the time? Okay. So logistic regression is just assuming something about the ratios of probabilities, and there's another point of difference. One is that it did not make any assumption about the distribution of x given g, which is what LDA did. Another distinction is there is no closed form. You really need to do optimization to find, optimization to find beta hat else L is equal to 1 to k minus 1. So there are only k minus 1 times p parameters, unlike LDA, which had k. LDA had k times L parameters, the mu values, and the sigma matrix, which is p times p dimensional, and pi value. So there, all I'm saying is there are too many parameters on the LDA side compared to logistic regression side. Okay. Okay, and also need optimization, and also what is the loss function. Okay, so that's something that we have been avoiding in the past 3 models. The one with the linear regression, because we were just doing linear regression, the model was always residual sum of squares. The objective was always, the loss was always residual sum of squares. Even if we did linear regression for classification, we were just the vanilla linear regression just assumes least squares as objective. For LDA, the objective, I kind of didn't explicitly say this, the objective is going to be to maximize the likelihood of the data set. Okay. Okay, maximize the likelihood of training data. Okay. We'll get to this some other time. Okay, what the loss function is. So right now, both LDA and so LDA we already know the solution. How to compute the mu hats, so mu L hat and pi hat L and all that. I just gave the simple formula, right? They happen to be the solutions of not happen to be. They are the solutions of a particular likelihood maximization problem. So what is likelihood? Is the probability of seeing data given parameters. Okay. likelihood is nothing but the probability of x, x is equal to xi, and y is equal to yi given at a given parameter, whatever is the parameter. So in the so I just want to put a product here because I have n observations. So it's just saying this is not very important. Product is not important. Likelihood is nothing but I'm trying to find for the best parameter, right? The parameter of in LDA case was sigma, mu's, and pi's. The parameter for logistic regression is going to be all these betas. So find a parameter such that the probability for that parameter, the probability of x and y's that I observe in my data, the n such x and y's, x and g's actually, is maximized. Okay. Now this is the I guess the complete likelihood because it's looking at a joint distribution between x's and g's. I put a condition in bracket here because for logistic regression we are not thinking about the joint distribution. So in logistic regression's case, we'll maximize the usual thing, which is going to be the equivalent corresponding thing, which is going to be pi is equal to 1 to n of probability of whatever is the parameter of g is equal to gi given x is equal to xi, because that is the only model we assume, right? In the sense of we assume something which only led to some expression like this, which only involves g given x. Okay, that's why I said conditional likelihood. So likelihood is a loose term to just say likelihood just means some probability, and in particular it's probability of observing a training data at any given model parameter value. So these two are not the same, but what I'm saying is either likelihood is this in the LDA case and likelihood is this for logistic regression case. Okay, you somehow maximize this. Okay, let's not worry about it. We'll kind of revisit this idea, I think, once more. So we'll kind of ground it again. Any other questions? Okay, in the last 10-15 minutes, I'm gonna revisit the topic of model selection. Sorry, revisit the topic of cross validation, but just put it in the broader context of what is the typical terms people use. So people use the words model selection and assessment. Okay. Okay. Assessment just means what is the EPE or something equivalent to EPE for a model f hat. Let's say you used your data, found a model f hat. What is the performance of that model, right? So you remember, so something like, I want to just know what is the test performance of this model. That's what it means. What is the out in the wild, performance of this model? That's assessment. Model selection is the issue of choice making. Okay. It could be the choice of should I use LDA versus logistic regression versus linear regression? It could be as different as that. Very different models. Or it could be within a single model class. What is for example, I'm going to just fix with ridge regression. What is the choice of lambda? Okay, these are all choices that you need to make. So once you make a choice, you are essentially selecting a model class or a set of models which you're willing to consider. Okay, So if you make a choice to pick logistic regression models, then that's a choice across models, across model families. And if you make a choice of lambda, that is also essentially a choice of model families, because lambda influences what is the search region. So I was just talking earlier, if you choose lambda to be really big, then you're looking for models only in a really small area, and if lambda is really small, then you're essentially looking at the whole region of betas for a model. Okay. So that's also choice. That's also concerned of model selection. Okay. Yeah, and the notes has some description about what we already know, so let's not worry about it. Bias variance decomposition, fine. Okay, so one choice, one technique that we've already seen is called k-fold cross validation. I'm going to revisit it, but there are a couple of there's another alternate methodology which I personally don't really prefer. I don't personally prefer, but it's something which people have worked out traditionally. It's called AIC and BIC. Okay, these are, I guess I should expand it, AIK and Bayesian information criterion. Okay. So what does it mean? So what is this other choice? So here, what is this other strategy? The strategy is you want to figure out for your choice, right? You want to figure out which choice is the best choice, and like you make a choice of subset. Which subset is the best one? That's the model selection problem. K-fold cross validation thinks of creating these validation sets. Don't use your whole training data, or like make it into folds, keep a fold apart, train only on the other folds, do something, evaluate on one held out fold. Some notion of validation is there. AIC and BIC based methods, or these methods, they don't think of a separate validation data at all. Okay, you've been given training data, just fit a model. Okay, but the way you're going to score the model is that you will have, if you fit a model, let's say you fit a model, then that will have a training error or loss value, right? Let me just call this ERR bar, which is just the, I'm going to normalize it this time. So I'm going to, in this normalize just means I'm going to divide by 1 by n, sum over I is equal to 1 to n of some loss. Okay, loss of a model. I don't want to use beta because it's more general. So let's say some model theta over my data. Data is going to be xi, yi, 1, I is equal to 1 to n, let's say. Okay, some model. I'm just generally writing that you will have some, like this could be residual sum of squares, right? Then this will be beta, and then you will precisely know what exactly this is, right? What AIC and BIC do is they are trying to add a bonus to ERR bar to get an estimate of EPE, okay, or an equivalent of EPE basically, which is going to be expected loss over test over expected loss. Okay, it may not be just residual sum of squares. It could be for this loss, what is the expected error. Remember, cross validation was only trying to estimate the EPE if it was in the case of residual sum of squares. Similarly, you are always going to estimate the performance of your model on a new data point. Okay? So let me explicitly write what EPE is. So estimate of the expectation of P of xy over loss of theta on x and y. Okay, whatever this x and y is. In a sense, for any new data pair like that is drawn from this joint distribution, which you don't know, the model that you picked, how does it perform in expectation over this unknown distribution? That's what cross-validation was estimating a proxy for this. If you know this, then you can choose the best theta. Right? So what AIC and BIC do is add a bonus. And what is that bonus term? So let me just write it for AIC. So they add a bonus such that this training error plus the bonus somehow roughly approximates a number which is close to this. Okay? Because this is the number over which you need to decide which is the best model for you. Right? How do different models do in the wild? And among them, I'm going to pick the one model which does well in the wild, on test. Right? So AIC says, okay, just do ERR bar plus this is quite arbitrary, but T2 by n times some sort of let me put parameters, some function of parameters times sigma hat square. Okay, so what are these things? Okay, 2 and n are anyway constant. That's the number of data points. You need to know what is the number of parameters in your model. Okay, some function of number of parameters in your model. So if you're comparing let's say linear models, then it could be the number of coefficients or something like that. So this is model dependent. So I'm just generally writing it as some function of parameters. Okay, how many parameters do you have? Okay, so the more parameters, you will have more test error roughly. It's basically saying you're potentially going to overfit. So that's the intuition here. So if you have too many parameters, you may whatever training error may be small, but this will offset and maybe give you high test error. That's why there is a linear dependence on essentially the number of parameters. Okay, and sigma hat square is just some sort of a residuals. It's just fit a model, then just look at all the in-sample errors. Right? You had the true value, the predicted value, difference between them, sum them, square them. It's this essentially. So anyway, these are all model specific, and to get the exact value here, you need to know which model class you're working with. So some offset like this. AIC gives an offset like this, and BIC also gives an offset like that. It's gonna be ERR bar plus 2, okay, not 2, but again d parameters times log n by n. Okay, there's also same thing, sigma hat, let's say. Okay, that's also a sigma hat square. So I guess qualitatively you need to understand there's an additional log n penalty with BIC, and there's the way I'm presenting it here, it looks like this seem to be quite arbitrary bonuses that I'm adding, but traditionally there's been some motivation in terms of why such a penalty makes sense and why this term may sometimes be a really good estimate for some quantity like this. But we are sidestepping all that because I think for this class we're just gonna stick with cross validation as the primary way to decide between choices. Yeah.
Would it make sense to think that AIC, BIC were ways to come up with errors in the models before it was easy to do computationally cross validation?
Yeah, that could be one reason. Yeah, before more numerically focused methods like cross-validation. Although cross-validation also people have come up with theory of why it estimates things like this properly, right? But these are just offsets. So there's no notion of validation here. It's just pick something on your training data and then add these bonuses because you are using too many parameters or too less parameters, such that you kind of get a guess of, such that you can decide between models. Okay. Actually, yeah.
So if you have more parameters, then that can tell you what model to use, and if you have less parameters, that can
Yeah, it's basically penalizing. It's saying, the true, if you have too many parameters, it's going to have a huge bonus here. Okay. So it's going to say don't take that model. You want to have, it's basically saying, it's again the same idea, right? You want to pick the one with lowest such out of sample loss, right? So in the cross validation, what are you doing? You're getting scores for different choices, and you're picking the one choice which has the lowest such proxy score. The score was an estimate of a quantity like this. Okay. Similarly, in this case also, you will have such scores for different models or different different models, and then you pick the model with the lowest score. There's some cautioning about cross-validation in my lecture note, but essentially the caution is as follows. I think we have 1 minute to do so, and the caution is as follows. You should not do pre-processing. So you typically, when you get a data problem, you're going to look at scatter plots maybe with respect to input and output. Okay. Don't do the scatter plots and then do cross-validation. Do those scatter plots as a part of your cross-validation. Okay, that's the basically gist. And why is that? Is because if you look at scatter plots and take some informed decision, you're basically, like for example, you look at scatter plots and you really think that looking at scatter plots, you really see that one of the variables has nothing to do with y, then you will drop it. Okay, so you made a choice right there. Okay, you dropped it. And then for something else like subset selection or maybe ridge regression, then you're doing cross-validation. Okay, that's the wrong strategy. Okay, you should do anything to do with input-output plots as a part of a cross-validation. So break up your training data, look at 4 folds, then do the scatter plot, and then see whether in those 4-fold based scatter plot if y is related to x, and maybe you manually delete something, like maybe delete a variable. That's fine. Okay. So what I'm saying is don't precede choices. Like try to include as many choices inside the cross-validation loop as possible. Okay. That's the idea. Otherwise, you'll be off. I don't know how many of you followed it, but if not, look at the description at the end of the note. And try to follow, if you're not following ESL, Elements of Statistical Learning, try to follow the other book for sure. Okay. Element of Statistical Learning is not really needed that you have to go through that if you follow the Introduction to Statistical Learning with our book. Okay. Okay, that's it for today's class.